it's time to contact Wagner and Manuel and Konstantinos. Please stand up. Where are? There. Okay. So these are the experts in getting Orca to go. I think last time, so you should not postpone this. Try to get it to go, and if you run into problems, ask them so we can figure out the problem before Sunday or Monday when it's time to use Orca. I think, oh yeah, one more thing. Many of you may have seen that and may already know where the poster session is. You just take the stairs up to the third floor. You turn left, you are on the so-called River Bridge that connects to the chemistry side. On that bridge, there are lots of poster boards and easels. Find your number for your poster on the latest document on Dropbox. Put it up at your leisure. Poster session is on Friday. Okay?
Good. So welcome back, everybody. I did not expect to see more than half of you here in the second half, but so you're very, very generous crowd. I appreciate that. So I guess the second lecture now will have a very different character from the first one. So in the first one, we have been going to setting like a conceptual framework how to interpret electronic structure and spectroscopy of transition metal ions. Now, as all of you know, that chemical journals these days are littered with theory. And that has a reason, and the reason is that first reluctantly, but now in a more stormy fashion, theory has found to be useful for chemistry, and actually in all branches of chemistry, including biochemistry, including coordination chemistry, including spectroscopy, including supramolecular chemistry, including organic chemistry, metallo-organic chemistry, or catalysis. And the reason for that is that using a computer these days, you can greatly guide your chemical thinking. But that also implies that you want to think. It's, yeah, it is basically infinitely easy these days to get your hands on a quantum chemical program package. So they are out there, they are either for free or they're not expensive, and within a few minutes you can get going and you can press the enter button and you get some numbers, and then you can believe whatever the computer wants to tell you. But that is not the way to do it, right? If you're a scientist, you're being critical. And occasionally, these things that the computer tells you are also wrong. And it's extremely important that you make contact with the real world. Spectroscopy is a fantastic way to make contact with the real world. And it is also necessary to some extent that you have at least an elementary appreciation of what these programs are doing. And that is the purpose of this lecture. I guess we all drive cars, and if you're like me, you don't understand much of how the car works, but you know how to drive it. And the same is, say, with NMR spectroscopy. Every chemist knows how to operate an NMR spectrometer. Very few really understand deep down the physics that's happening inside the spectrometer. And that's totally okay. That's totally okay. You just have to know how to use it properly. And so what we're going to talk about here in the next hour and a half is like a bird's eye view of what really is happening in these programs. And you can take it from there. And obviously there is a tutorial part here, and I hope that many of you take it and gain some familiarity. But one thing it will never free you of, and that is being critical towards your own results and ask yourself, backcheck with reality whether it makes sense. If you use it in an educated and careful fashion, computation can be your best friend in chemistry, whatever branch of chemistry you're working in. So, having said that, let's listen to what the philosophers said about the possibility of computing any chemical phenomena. So here's that guy, Isidore Comte, and in the late 1900s, even shortly before quantum mechanics was invented, he said any attempt to use mathematical methods for the investigation of chemical questions must be considered as completely irrational and is strongly opposing the spirit of chemistry. If mathematics will ever occupy a prominent place in chemistry, an absurd idea that fortunately is completely unrealistic, this would lead to a rapid and irreversible decay of this scientific discipline. Wow, you see, that is the difference between philosophy and science. And in philosophy, you get away with anything. As long as you say it with enough sonority and authority, you will have your following. In science, you have to present the evidence. Well, the evidence was counter that guy. And a few years later, quantum mechanics was invented. And today we are standing on the shoulders of the giants who have found or invented quantum chemistry, Schrödinger, Heisenberg, and Dirac, who managed to bring relativity, the theory of relativity, into quantum mechanics. Interestingly, we talk about the Schrödinger equation as a fundamental equation of quantum mechanics, but as a matter of fact, what we're doing these days is quantum mechanics much more along the lines of Werner Heisenberg. So it should be at least the Schrödinger-Heisenberg equation, but it is the Schrödinger equation. Actually, Heisenberg really didn't like Schrödinger, and it's very interesting to read about some letters he's written to Pauli and others in the time. So if you have like a rainy Sunday afternoon, it's very entertaining to read about these days. So, but very shortly after that was done, Dirac, who wasn't the most outgoing person on the planet, he made a very strong statement. It was almost as strong as the one from that philosopher. And he said the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. I mean, completely is a strong word, right? And the difficulties lie only in the fact that applications of these laws leads to equations that are too complex to be solved. So he basically said that fundamentally and conceptually the problem of how to compute any property of any matter is solved. And to the best of the knowledge we have today, he was absolutely and completely right. And so he figured it's just more or less an engineering problem, like to solve these mathematical equations he's talking about, which happens to be his own equations, of course. And he followed it up with a less well-known statement saying, hence it would be desirable to develop practical approximation schemes for the application of quantum mechanics. That basically has been the agenda of theoretical chemistry for the last 90 years, and I think huge progress has been made. But we're, of course, nowhere near the point where we can compute everything. Of course, we shouldn't even try to claim that we can compute everything. There are gentlemen like this person, Enrico Clementi, is still around, was a great pioneer, has done very important work in the 60s. And already in 1975, he claimed we can calculate everything, and in the following, there was like overboarding optimism of what you can do with a computer, and equally extremely bad science was produced, leading to rapid and fortunately reversible decay of the discipline. There was a lot of very poorly done theory. I think now, today we have a more realistic view on things, and I want you to grasp the gist that you should use it as a partner of experiment, not to replace it. So if you think that you can prove anything with a computation, that's not correct. It's philosophically not correct. Remember, Max Planck said that experiment is the only source of knowledge. The rest is poetry and imagination, referring to theory, and obviously he was a pretty good theoretician. And so view it like Max Planck said. View it as a partner of experiment, get insight, get new ideas. If the theory leads you to a new idea. But do not hit the enter button and believe everything the computer says. That's not the right way. So why would you want to do quantum chemistry? So you want to do quantum chemistry in order to predict quantities that simply cannot be measured. For example, if you have a chemical reaction and pass the rate limiting step, there are 4 or 5 different intermediates. They will never build up to any measurable quantities. Then sometimes computation might be the only thing that's possible. So non-accumulating intermediates, that's one possibility. Then very important, interpret the outcome of experiments. For example, NMR, but even more so EPR spectroscopy has like reached the stage where you can get spectra in amazing resolution. And then you sit on a huge pile of data, and there is no way you're going to be able to interpret this without the help of quantum chemistry. And it is here where partnership between theory and experiment is extremely strong. You can use theory in order to obtain insight into the trends and regularities of data. And I think that, in my mind, is like one of the most important aspects of how you can use theory. It's not that much to produce numbers, but to produce an intuitive understanding of the systems you're studying. Very good theoretician Mike Zerner, he once said, like, the best computations are those that after I did it, I understand that I wouldn't have needed it. Think about it. I mean, there is a lot of truth in that, and there's a lot of wisdom in that. Yeah, so you want to ask your computer more than to just give you a number. Yeah? And that is also why you heard me talking about ligand field theory. You can marry these two things. They're not mutually exclusive. They're complementary. You can also use the computer in order to predict the outcome of future experiments. Very important these days. For example, industry is hugely interested in that, because if they ask themselves which of the 40 possible molecules should I synthesize to achieve a certain property, say, given color or whatever, they would love to be able to make it on the computer first, which is much cheaper, and then only try the best 3 candidates. This is the direction it's quickly heading, and it's a very, very productive way forward. There are many, many other reasons why you may want to do quantum chemistry, not the worst one of which it's really fun, and I hope that you can catch some of the fun in your tutorials. So now let's look at what's really happening here. And the almost irresistible simplicity that underlies the problem is, the promise here is that you basically only need one single physical law in order to explain all the behavior of matter, all the complexities of chemistry, all the complexities of biochemistry. Whether you have a solid, or whether you have an organ or a cell, an enzyme, a supramolecular complex, it's all the same. It's one physical law. And the one physical law is Coulomb's law, that states that the interaction energy between two particles with charges Q1 and Q2 is simply Q1 times Q2 divided by the distance between the two particles, the inverse distance. Yeah? And that's it. So in terms of, if you look at a molecule through the eyes of a physicist, it simply consists of positively charged nuclei, negatively charged electrons. The nuclei repel each other, the electrons repel each other, and the nuclei and electrons attract each other. That's basically it. That's all there is. That's all there is to chemistry. And so it is like a billiard game with like charged particles, and they all buzz around. The only other thing that comes in addition is the kinetic energy of these particles. So they have a velocity, and hence they have a momentum. And before you take into account relativity, this is all of the physics that there is. So the only thing that you need is to take the quantum mechanical version of that in principle simple physics. Now I should make a statement here. Obviously, like we have many electrons and many nuclei in a molecule. Now, in Newton's days, when they were worrying about planets and their interactions, they already realized that a system that contains 3 particles is very hard to deal with, and you will not find a closed-form solution. Then came quantum mechanics, and you couldn't solve in closed form a problem with 2 particles. Then came relativistic quantum mechanics. You couldn't solve in closed-form systems with a single particle. And then came quantum electrodynamics, and you could not solve the equations for no particle. And so this is how progress was in theoretical physics. But the reality is of which these things applied properly are incredibly accurate. There is not a single known deviation from the predictions of these theories. Okay. So that means we need to make a transition between the classical physics and the quantum mechanics. And so the best way you can connect that is with a formalism that was worked out by an astronomer called Hamilton. And in these days, he took Newton's equations and reformulated them. And so for a classical system, if you characterize it completely, you have to know the positions and the velocities of all particles at time 0. And then you solve the Newton's equations of motion, and what you get are the trajectories, and the trajectories consist of the solutions are the positions as a function of time and the momenta of the particles as a function of time. That is, then if you have that, you have complete knowledge about the classical system. In quantum mechanics, you know that we cannot have that because of the uncertainty principle that forbids us to simultaneously know the positions and the momenta. So instead of these trajectories that you have in classical physics, you have the many-particle wave function that we will talk about later. And the many-particle wave function, that provides us with a probability of finding these particles at a given point in configuration space with given velocity. More details later. And in Newton's days, the classical system was best solved with the Hamiltonian formalism. So the Hamiltonian of a system simply corresponds to its total energy. That means you simply write down all the terms that contribute to the total energy of the system. Now let's be so bold and just do that for the system we have just seen, charged electrons and nuclei. So you have the kinetic energy of the electrons, that is the sum over all electrons, the momentum squared divided by 2 times the mass. The same for the nuclei. Then you have in SI units the electron-electron repulsion, the nuclear-nuclear repulsion, and the electron-nuclear attraction. That is all there is. That is 99.99% of all chemistry once we translate that to quantum mechanics. And so when you make the transition from classical to quantum mechanics, first thing you do is you pass on to a special set of units. And these are called atomic units. And in atomic units, they have the nice property that the values of all of these fiddly constants that you have are unity, 1. So h bar equals 4 pi epsilon 0 equals the elementary charge equals the mass of the electrons are set to 1. And the only physical constant that has a different value is the speed of light, 137.06. Now, that will also lead you to the unit of energy being the Hartree. So a Hartree is a pretty big chunk of energy. It corresponds to 27.2107 or so electron volts, or 630 kilocalories per mole. You will later see that this is a big problem in the application of actual quantum mechanics, that the Hartree is such a large energy unit. So, second thing is, you don't have to do it this way, but it's infinitely convenient to pass to atomic units. But now when you pass from classical physics to quantum mechanics, you have to replace the momentum of a particle by its quantum mechanical analog, which is minus the imaginary unit times the gradient operator. And that is already it. The third thing that you need to do, and we do it here in a phenomenological way, but it would fall out of Dirac's equations in a very natural way, is to introduce the spin of an electron. So the electron is not only moving in a 3-dimensional space containing x, y, z coordinates, but there's a fourth coordinate, which is the spin of the electron. The spin space the electron moves in is a very odd space because it's a discrete space where the electron can only assume like 2 possible values, which is plus minus 1/2. And I don't want to go into mathematical subtleties here. You can basically think of an electron as having spin alpha or beta, and we looked at the consequences of that in the last lecture already. So, given all this, the fundamental equation for determining the maximum you can know about the system are no longer Newton's classical equations, but is a Schrödinger equation. And as I said, the role of the trajectory is taken by the many-particle wave function. And so the Schrödinger equation for the many-particle wave function psi is the following. And I will introduce psi later, but for the time being, say that psi consists of the n sets of electron coordinates, where each x contains the spatial coordinates, x, y, z, as a spin coordinate sigma, and the m positions of the nuclei and time. Yeah? So that is a time-dependent Schrödinger equation here. It's I times the first derivative of the wave function with respect to time equals the action of the Hamiltonian, so that is the Hamiltonian operator onto the wave function psi. So we're talking about stationary states here. The spectrometer also sees transitions between stationary states. And so especially if the Hamiltonian itself does not contain time explicitly, you come to the time-independent Schrödinger equation that simply reads the Hamiltonian operator H applied onto the wave function psi equals the total energy times the wave function psi. So in other words, we are looking for many particle wave functions psi that are eigenfunctions to the Hamiltonian operator. So that is a formidable problem, and so we need to make chains of approximations. And the first approximation that we make, and that is actually an extremely important approximation, is the so-called Born-Oppenheimer approximation. The Born-Oppenheimer approximation consists of throwing away the kinetic energy of the nuclei. So what that means is we consider the nuclei of the molecule at rest. So there is rigid framework of nuclei in which the electrons move. And when we change the position of each and any one of these nuclei, the electrons are immediately following. That is essentially the Born-Oppenheimer approximation, and it's like back-of-the-envelope justification is that the nuclei are much heavier than the electrons, and hence they move much slower. That has a very important consequence. The consequence that you can write down a chemical structure, you can draw it on paper, is only possible after introducing the Born-Oppenheimer approximation. If you have the picture that all nuclei are constantly moving, you cannot pin down a chemical structure or chemical connectivity. So the Born-Oppenheimer approximation is absolutely essential for applying quantum mechanics to chemistry. It has many interesting consequences. I will only say that in parentheses. So if you analyze it mathematically, the Born-Oppenheimer approximation is a mathematically divergent series expansion. So it cannot even be rigorously justified, despite the fact that it is absolutely essential to do quantum mechanics on molecules. The second consequence is that the Schrödinger equation separates into two equations, one for the electrons at any given arrangement of the nuclei, and one for the nuclei on a given potential energy surface. And that is the one that we will talk about tomorrow when we talk about vibrational spectroscopy. And today we will only talk about the electronic part of the Schrödinger equation. Yeah, so we're looking at the wave function at fixed position of the nuclei. That is this like vertical bar times r. That means we have the wave function at any given arrangement of nuclei. So, is the Born-Oppenheimer approximation any good? And the Born-Oppenheimer approximation actually is very good. It describes almost all of chemistry, almost perfectly. There are a few exceptions and a few extensions. Now, since there are no terms in the Born-Oppenheimer Hamiltonian that contains interactions of nuclei and electrons with external electric and magnetic fields, that means we need to extend it if we want to interpret spectroscopic experiments. It misses many of the small terms that are associated with electron and nuclear spins. They all come out of the theory of relativity. It does assume a point-like nucleus, and those of you who are involved with Mössbauer spectroscopy know that you need more than that. The nucleus is not a point nucleus. For most of the purposes of quantum chemistry, you can treat it like a point nucleus, but in reality it's not. And you will need to go beyond it if you talk about nuclear properties such as a quadrupole splitting. The Born-Oppenheimer-Hamiltonian breaks down in a very few specific areas, and that is where the separation of nuclear and electron motion is no longer separated. That happens in, for example, the dynamic Jahn-Teller effect. Yeah? So when you treat the Jahn-Teller effect we talked about in the last lecture, mathematically rigorous, and like you go into the very fine details of spectroscopy, you will need to go beyond the Born-Oppenheimer approximation. And you will need to add some relativistic terms. That seems to be a bit odd, but in like any transition medal calculation, you will need to take care of relativity in one way or another. That includes the first transition row. And it has been neglected for a long time in very many calculations, and there are inconsistent calculations that are pretty bad quality because no account was taken of relativity. One example in bioinorganic chemistry is the copper dioxygen chemistry, where you get literally wrong results if you don't include relativity in one way or another. Okay, but for the moment we are staying in the framework of the Born-Oppenheimer-Hamiltonian, and we're happy with it. So now let's look at what does it mean. So if, say, pretend we can solve that Born-Oppenheimer-Schrödinger equation. Now, we get a many-particle wave function. What is that many-particle wave function? And the interpretation of that many-particle wave function is the following, that given a nuclear configuration R, the square of the many-particle wave function psi gives you the conditional probability for finding electron 1 at position R1 with spin sigma 1, and at the same time electron 2 at R2 with spin sigma 2, and so on and so forth. Yeah? So it's a conditional probability for finding the sets of electrons, nuclei with given spins at a given configuration in space. That is an amazing amount of information, and it's actually much more information than you ever need. So modern ways of trying to approach quantum chemistry are trying to never having to know that many-particle wave function because it's an information overkill. There are actually not that many things we really know about that many-particle wave function, but one thing we know for sure is the Pauli principle. And the Pauli principle requires that if you interchange the coordinates of two electrons, say xi and xj, the wave function has to change its sign. Now, at the end of the day, you will square it, and then that sign will disappear. But that anti-symmetry with respect to particle interchange, it's an absolutely super fundamental property of matter. It's never violated. It is completely strange, and there is no physical picture behind it, but it is absolutely certain that the Pauli principle never fails. Now the question is, how do I picture the many electron wave function? So I've written here this thing that's like psi of R1 sigma 1 blah, blah. So what's the picture? Like, what picture should I have in my mind? And the answer is you don't have to have one because nobody has one. Yeah. So a wave function that consists of n sets of particle arguments is an object that's so complicated that nobody has a picture of how to do that. Yeah, if like you think that psi has anything to do with orbitals, you're wrong. We're not talking about orbitals here. We're talking about many particle wave functions, and interpreting a many particle wave functions intuitively is not happening. Yeah, so the insight, like making chemistry out of that thing is a different challenge. We're getting there, but at that point you should say the many particle wave function is what you get. It is normally too complicated to be interpreted. The second thing you get out is the total energy. So what is the total energy? The total energy obviously depends on the arrangement of your nuclei. And does it have a physical meaning? Yes. And what is that physical meaning? The physical meaning of the total energy is that it is the energy that is required to separate the molecule into non-interacting nuclei and electrons, not protons and electrons, nuclei and electrons. That, of course, is a physical observable. In practice, it is not a physical observable because you never do that experiment that you like bust up your molecule until you have like separated electrons and protons. So in chemistry and as well in spectroscopy, you measure energy differences. Yeah, and so calculating energy differences is much easier than calculating actually total energies. I will come back to that in a second. Now, how large is that total energy? That is quite a large number. And I've just put down something. For a typical transition metal complex, it might be 10,000 to 100,000 electron volts. And now the big question is, how accurately do we need to know that number? Now here where it comes into play that you have to have at least one system of energy units that you feel comfortable with. And yeah, it is necessary. You have to have a feeling of what is a large energy, what is a small energy. Now, a chemical bond, say CH bond or so, has an energy of about 100 kilocalories per mole. So you need an accuracy of about 1 kilocalorie per mole in order to predict chemistry properly. Because for every error that you make of 1 kilocalorie per mole that you make in the energy, you would come up with a rate constant that's off by a factor of 10, redox potential that's off by 60 millivolts, or an equilibrium constant that's wrong by an order of magnitude. So 1 kilocalorie per mole corresponds to roughly 0.05 electron volts. So you need to calculate these 100,000 electron volts to an accuracy of 0.05 or better than 1 part in a million. And it is that curse of quantum chemistry that we have to be so damn accurate to be useful. Yeah, then it really is a curse. It is actually really easy to calculate 99.9% of the correct energy, and it is absolutely hard to calculate the energy to that accuracy that you need for chemistry. We will come back to that later. Now, obviously, the Schrödinger equation, the Born-Oppenheimer Schrödinger equation, has more than one solution. Yeah? So there is more than one eigenfunction. There is more than one total energy. In fact, there is a whole spectrum of eigenfunctions and a whole spectrum of total energies. So hence, we have to label these solutions. And you start with 0. And that means E0 is the ground state total energy of the system, and EI of R, for I larger than 0, are the excited states of the system. Yeah? And that means each state also has a separate many-particle eigenfunction psi of I. Yeah? Now, if two or several eigenvalues are identical, you said that the state is n-fold degenerate. And the eigenfunctions belonging to the same degenerate eigenvalue are only determined up to an arbitrary unitary transformation. That means if you have two wave functions that belong to a degenerate eigenvalue, you can take a linear combination like 1 over square root 2, 1 plus minus the other, and you end up with the same physical content. So, if you do it with a computer, the computer doesn't know what to do, and it will come up with an arbitrary combination of those two. That is important to keep in mind. Yeah, and now we're coming back to the very beginning of the first lecture and say these eigenfunctions of the Born-Oppenheimer Hamiltonian can be classified according to the total spin, the spin projection quantum number, and the overall spatial symmetry. Yeah, so this is what you can say in general about these solutions of the Born-Oppenheimer Hamiltonian. Now, there also is the dependence on the nuclear coordinates, and here is where chemistry comes into play, because if you study the variation of the eigenenergies as a function of nuclear configuration, you come to potential energy surfaces. And you will need to calculate potential energy surfaces if you want to make theoretical statements about chemical reactions. And so you are looking for points of these potential energy surfaces that are true minima. How do you know what a true minimum is? you calculate the second derivative of the energy with respect to all nuclear coordinates. That is the so-called Hessian matrix. And if that only has positive eigenvalues, you know you're in a minimum. Do you know when you are in like the global minimum, so the lowest possible energy you can achieve for any nuclear configuration? You never know that. So, but any chemical structure is a local minimum on the potential energy surface. How stable it is a different question. So you have reactants are one minimum, and products of a chemical reaction are another minimum. Then the energy difference here is the reaction energy. Now, before you can compare this to, say, a thermodynamic measurement, you need to turn this into a free energy. So we're only talking about the electronic energy here. There are various terms you need to add before you can come to something that you can actually compare to something that somebody has measured, say, with calorimetry. Now, when you go from the reactants to the products of a chemical reaction, you will have to pass through a transition state. That is a saddle point on the potential energy surface, and is characterized by a single negative eigenvalue of the Hessian matrix. Yeah? So what that signifies then, it's a saddle point. If you have more than a single negative eigenvalue, it means you're not at a true transition state. The energy difference between the reactants and the saddle point, that is the activation energy, and it goes into the calculation of the reaction rate. Yeah? So that is basically how you compute chemistry. You compute equilibrium constant by computing reaction energy, and you compute rate constant by computing activation energies. In terms of spectroscopy, most spectroscopy is calculated, but not all, is calculated at fixed geometry. You vary about the energy of all of the excited states at a given nuclear configurations. Now, as you know, with the photon, you can induce transitions between the ground state and all of the excited states, or even between excited states with each other. And the probability for such transitions is correlated to the intensity of the peak you see in your spectrometer, which is in turn governed by Fermi's so-called Fermi's golden rule, which tells you that the intensity is proportional to the matrix element squared between the initial state, typically the electronic ground state, and the final state, and H1 is some perturbing operator that tells you what type of radiation molecule interaction you have. So that's an electric field, electric dipole, or electric quadrupole, or magnetic dipole operator. So this is how spectroscopy works. So now we have covered thermochemistry, we have covered kinetics, and we have covered spectroscopy in principle. So that is the overall framework of what, what you have to do. And in principle, that allows you to connect not only to all of thermochemistry and kinetics, but also to all of spectroscopy. And when you discuss spectroscopy, it is really, really important that you remind yourself what energy scales are you talking about. So spectroscopy in bioinorganic chemistry starts at energies of about 14,000 electron volts with gamma rays used in Mössbauer spectroscopy, and ends with about 10 to the minus 7 electron volts, which are the radio waves used in Endor or NMR spectroscopy. Yeah? So that is about 11 orders of magnitude in photon energy, which correspond to very, very different chemical phenomena. But keep in mind that the energy of chemical bonds is roughly in the region of 1 to 4 electron volts, where you have UV visible spectroscopy and absorption spectroscopy, MCD and CD spectroscopy. So with these spectroscopies, you directly look into the chemical bond. Yeah? Everything else is looking into the consequences of chemical bonding. And before you sit down and learn about the theory of any spectroscopy, make sure that you have your energy scale properly sorted out and you understand where in the hierarchy of molecular phenomena that spectroscopy is located. Yeah, for your information, one atomic unit, as I said, is about 27.21 electron volt. 1 electron volt is about 8,095 wave numbers, is 23.06 kilocalories per mole, and one wave number is about 30,000 megahertz. These are things that are important to know so that you understand we're all talking about the same things. So now the nice question is, now that we have that, and in principle it gives us access to basically everything we can measure, the question is, how do we solve the Born-Oppenheimer-Schrödinger equation? And the answer is unfortunately not at all. It cannot be solved in closed form for any system but one electron system. So if you had physics like in your curriculum, you know, you went probably through the solutions of the hydrogen atoms, and that is what you can do. But not even for the helium atom can you solve like the Born-Oppenheimer-Schrödinger equation exactly. That means you need approximation methods. Now, the best approximation methods become pretty damn good these days, but you should keep in mind that nobody has ever generated an exact solution here. And so at that point, you have to familiarize yourself basically with a zoo of quantum mechanical methods, at least on a surface level. So here's our physical problem. That is the Born-Oppenheimer problem. Now, the systematic approach to solving that is to start from a much simpler model, which is called the Hartree-Fock theory that we go into in a moment. That gets you there about 99.8% of the way. And that 0.2%, owing to the largeness of the total energies, is not good enough, so you need to follow it up by corrections to the Hartree-Fock energy. And they fall into two flavors, and one flavor is the so-called single reference correlation methods. They go by names like configuration interaction, many-body perturbation theory, or coupled cluster theory, where, like, the world of theoreticians has sorted out that coupled cluster theory would be the preferred way of doing quantum chemistry. At that point in time, it is too expensive, but methods have been developed so that you're sitting here and probably you're having in your mind papers that are saying theoretical chemistry or quantum chemistry equals density functional theory. That is true today. That will no longer be true in 5 to 10 years from now, just because there will be methods available that get better results in a similar time and you get the right answer for the right reason. In principle, you can approach the exact solution of the Born-Oppenheimer problem almost arbitrarily closely when you follow that hierarchy of methods. If you have more complicated systems like transition metal complexes typically are, you need extended versions of that go by the name multi-reference, but I don't want to go into that. Now, this is a systematic way of solving that equation. We will, at the end of this lecture, come to the theory of density functional theory, which at this point in time is dominating computational and theoretical chemistry. It is in principle based on the promise that you don't need to do all of this hard work, but that you can basically get the exact energy without ever solving that equation at a computational cost that is similar to Hartree-Fock theory. That leads to a lot of semi-empiricism, also good semi-empiricism, but also very bad semi-empiricism. And when one applies density functional theory, one should have a firm understanding of what it is and what it is not. It is nevertheless an extremely useful thing to have in the arsenal, but it's only one out of many approaches that you can have towards the electronic structure problem. Now, if you throw away the quantum part of it, you can, of course, simplify it to the level of force fields that you use in large-scale simulations, and people like Klaus Schulten talking about, like, simulating entire viruses or whole cells with millions of atoms on the basis of these force fields in an atomistic fashion, so that is happening. And at an intermediate stage, you have parameterized versions of Hartree-Fock theory, semi-empirical methods, but that at this point in time, they're not very popular. So most of the theoretical methods that you're likely to run into are either density functional theory or coupled cluster theory or force field calculations, or some combination of those. So I want to further your understanding of what these things are based on by discussing Hartree-Fock theory, and then we move over to density functional theory. So when you start about talking approximate methods to solve the Born-Oppenheimer-Schrödinger equation, what you have to have is a trial wave function. Yeah, so you know that you cannot solve the whole thing. You have absolutely no idea how the complicated many-particle wave function looks like. But what comes to your rescue is the so-called variational principle. So say out of your pocket or your mom's pocket, you pick a trial wave function psi trial, and you make it somehow flexible by putting some parameters p in. If you then insert it in the so-called Ritz functional, that is the so-called Ritz functional or variational functional, and you can make the energy now a functional of the wave function psi, the trial wave function psi. If your wave function psi happens to be the exact wave function, then E of psi is the exact energy. And for any other trial wave function, you can show that the energy that this thing is returning to you is always too high. But that is great, but that means you can build more and more flexibility into your trial wave function and minimize the energy, and you know you're always going the right direction. And so whatever your parameters is, the condition for a stationary point of that functional is that the first derivative of the functional with respect to the parameters is 0. Now you have to have an ansatz. So where do you start? We have that damn hard problem that we have to solve the Born-Oppenheimer-Schrödinger equation for a wave function that we cannot picture, and we need to find some starting point. And so what is it really that makes our life so miserable? And what makes our life so miserable is the electron-electron repulsion that we cannot deal with. If the electron-electron repulsion would not be there, then the n electrons in the system would simply behave like n independent electrons. And now we have a starting point. Let's just forget that the electrons repel each other, throw away the term from the Hamiltonian, and ask ourselves, what would be the many-particle wave function like if we had no electron-electron repulsion, and we would have n independent electrons? And that leads us to Hartree-Fock theory. Now, the first calculations that were done on atoms were based on such an assumption by a guy called Hartree. And what he did, he threw away the electron-electron repulsion, and he was writing, then using a mathematical theory of how to solve differential equations with separated variables as a product of one electron functions. So many particle wave function equals product of one electron wave functions. It actually, at that time, there weren't computers. So what Hartree did is he was using his father. His father was a retired engineer who liked to do math, and he solved these differential equations iteratively with paper and pencil. And these were the first atomic calculations that were ever done. The Hartree calculations had the big problem that they did not satisfy the Pauli principle. And the Pauli principle is so super fundamental to nature that you cannot get rid of it. And so what Slater did then is to basically take the Hartree model, so many particle wave function equals product of one particle wave functions, and repaired it by building in the anti-symmetry. And he did that by inventing the Slater determinant. So the Slater determinant is a determinant where you write the many particle wave function as a determinant where you have n one particle wave functions, psi 1 to psi n, and you have n sets of coordinates. And so now you permute which sets of coordinates you put into which of these one electron wave functions, and that makes a Slater determinant. There are n factorial terms in that. And this has proper anti-symmetry because if you exchange any one set of rows or columns of that determinant, it changes sign as it should. So, but physically speaking, it is nothing else but assuming independent particles. And at that point, we have introduced something important, namely one electron wave functions. Yeah, and these are just auxiliary quantities. Yeah, but these are the orbitals. These one electron wave functions are the orbitals, and they come from assuming independent particles, which allows you to write the many particle wave function psi as a Slater determinant consisting of products of one particle wave functions. So, what do we have to do now? What are these orbitals? Are they somehow there? They're not there, because at that point we have not said anything of how we obtain these orbitals. Actually, these orbitals, they are the thing we can vary now in the sense of the Ritz functional to obtain the lowest possible energies. Yeah, so think of it like a balloon that we squeeze a bit here and like extend a bit there and like put together here. So like we actually change the shape of these one particle wave functions to minimize the energy of the Ritz functional. What we get out of is of course not the exact wave function, but we get the best possible wave function that you can obtain under the assumption of independent particles. So we use a wave function of the wrong form with the right Hamiltonian, and we make the best out of it. That is the variational principle. And that is the Hartree-Fock method. And if that would not be enough, we cannot even solve the equations that come out of that treatment, because these orbitals have so complicated shape. And at that point, a person called Rothan came in, and in 1949, he suggested to expand these one-electron wave functions, the orbitals, in terms of a set of basis functions. It is very unfortunate that, like, the many chemical textbooks call this the linear combination of atomic orbitals. That is pretty nonsensical, because these basis functions here have nothing to do with atomic orbitals. Nothing, then is. Nevertheless, the only important point is you expand out of bare necessity these one-particle orbitals, and we call them molecular orbitals from now on, in terms of another set of auxiliary wave functions. Now, if that set is mathematically complete, that expansion would be exact. Yeah? In practice, we cannot have that, but we can get closer. That is then called the basis set limit. Any deviation from that is a technical mistake in the expansion of the molecular orbital in terms of basis functions. So in your practicals, you will use things like, when you read papers, there will be double zeta, triple zeta, quadruple zeta, whatever basis sets, and they have funny names like 631 GG star, whatever, and so on and so forth. These are different levels of not reaching the goal of having a complete one-particle basis set. Yeah? But in principle, you can extend these basis sets towards mathematical completeness. Now, there are people who say, oh, if I use this basis set, I get a better result than if I use that basis set, and then it's closer to experiment. But wait a second, that's not the right thing to do. Yeah? Because there is a well-defined basis set limit, and you only see the properties of your theoretical methods if you are at the basis set limit, which is what you should choose for, to have that set of auxiliary function as complete as possible. So now you have delegated the problem from like varying these unknown molecular orbitals psi directly to varying the expansion coefficient C. Yeah? So our unknowns were these things themselves. Now we have given these a definitive form. Now what we need to vary in order to minimize the Ritz functional are these coefficients C here, which are called molecular orbital coefficients C mu I. Now if you insert this into the variational, the Ritz functional, you get back the so-called Hartree-Fock-Rothan equations. That are the equations that you need to solve to obtain the molecular orbitals. This is a set of nonlinear equations, and they read the following. An operator F, which is called the Fock operator, applied to molecular orbital psi I equals epsilon I times psi I. So in other words, the molecular orbitals are eigenfunctions of a quasi one-electron, one-particle operator F with orbital energies epsilon I. So that comes out of the mathematical treatment of the independent particle model. Now, we will not do that here, obviously, but I will want to talk about what the physical interpretation of it is and what the quantities are that go into it. Now, the orbital energy epsilon I is you can view as the expectation value of the Fock operator for the given molecular orbital I. What it gives you is the average energy of the electron in the field of the nuclei and the average electrostatic field created by the other electrons. That is that funny two-electron integral here. And that two-electron integral here has two components. One is the so-called Coulomb integral, and what it consists of is the repulsion energy between psi I squared and psi j squared. So one electron is occupying orbital I, one electron is occupying orbital 2, j. These things are charge distributions. So the Coulomb integral is something entirely classical that is like the electrostatic interaction of two interacting smeared out charge distributions. It's obviously always positive since all of these quantities here are positive. So that makes sense, and it was the only thing that Hartree had in his equations because Hartree didn't satisfy the Pauli principle. But out of the Slater determinant ansatz, that meaning out of the Pauli principle, comes a second integral which is called the exchange integral. And the exchange integral is a quantum mechanical object that does not lend itself too well to classical interpretation. It is basically the self-energy of an interference density, which is a product of an electron in psi I and psi j. Now, you often hear people talk about the exchange interaction. There is no exchange interaction in nature. It doesn't exist. There never has been one. There never will be one. There is electron-electron repulsion, which is an entirely electrostatic phenomenon. It's the electrostatic repulsion of two electrons in conjunction with the Pauli principle that leads you to the presence of these exchange integrals here. You can relatively easily show that this is inherently positive and it comes with a minus sign, so it always contributes to a lowering of the total energy. Very importantly, that exchange integral is zero unless the two electrons in psi I and psi j have the same spin. Yeah, so that means the exchange integral only exists between electrons of the same spin. Hence, Hartree-Fock theory loves parallel spins. Yeah? Because then there is the exchange integral that contributes negatively to the total energy. Again, this does not describe a genuine exchange interaction. There is no such thing in nature. All of this is the consequences of electron-electron repulsion according to the laws of quantum mechanics. So this is then the physical interpretation of the Hartree-Fock model. Basically, you have an effective one-particle equation where each electron is swimming in the sea of the other electron. That's called the Hartree-Fock sea, and that's why it's also called the mean field model. And it sees the electrostatic field created by the nuclei. So now, obviously, in order to solve for the molecular orbitals, you have to know them, right? So in order to compute these integrals, you have to know what these psi's are. But you don't know them because you're about to solve for them. So that seems to be a bit counterproductive. And what then happens is you have to solve these equations iteratively. And so this is what you're doing when you run a calculation, and you will do it in your tutorial part. You will watch the computer printing iteration 1, iteration 2, iteration 3, iteration 4. Then it stops being fun, iteration 5, iteration 6. You see the energy, you wait for the energy to stabilize, and the energy is going up, the energy is going down, the energy is creeping, the energy is smearing, the energy is jumping, the energy is doing all kinds of funny things. But eventually you may get convergence. And then you have a Hartree-Fock solution. And basically what these computer programs are doing is they guess some starting orbitals, and then they calculate the Fock operator with the present set of orbitals, diagonalizing the Fock operators, calculating the total energy, check for convergence. If you're not converged, you keep doing this. Sometimes it takes 10 iterations, sometimes it takes 20 iterations, sometimes it takes 120 iterations, sometimes it takes 300 iterations. If it does take that many iterations, you did something wrong here with the starting orbitals, and you should look for a better solution. This is not entirely black box. You can help the computer program a lot babysitting it into a good solution. Yeah? If it converges, the program may print hooray, and it prints you your results or do additional calculation. Yeah? Convergence may be slow. You can help it. If you know what you're doing, you can help it, and you may need special techniques to reach that convergence. Now, let's look how good is Hartree-Fock theory. So now let's just for a second look at the Hartree-Fock calculation on the neon atom. That has 10 electrons. Now, for that 10-electron system, you know its exact total energy from experiment by simply summing up all 10 ionization potentials of the series. And so the exact experimental energy is minus 129.056 Hartrees. Now, Hartree-Fock theory gives you minus 128.547. I would say that's pretty damn good, isn't it? So it recovers 99.6% of the total energy. And if you subtract relativistic effects from that number here, it's 99.8%. And so most of the time you would say a theory that is 99.8% correct is a damn good theory. And if you want so, Hartree-Fock is a damn good theory, but it's not damn good enough, because this like 0.2% of the total energy that kills you, right? Because 1 Hartree equals 27.21 electron volts, and 1 electron volt equals 23.6 kilocalories. That means like 627 kilocalories. That means that small error of Hartree-Fock is already a 320 kilocalorie per mole error on the neon atom alone. And if I tell you that in order to do chemistry right, we need an accuracy of about 1 kilocalorie per mole, it's devastating, isn't it? I mean, we've been working so hard, we've been getting such a nice result, 99.8. We proudly clap ourselves on the shoulder, and then we come and say, well, not good enough. Then chemistry really doesn't work. So you see, I want you to appreciate how tough of a battle it is to compute these total energies to high accuracy. And it is also one of the reasons why I think it is much better, rather than relying on total energy calculations, to connect to the real world in terms of spectroscopy. Yeah? So, but we usually want relative energies, which is about 1 to 2 orders of magnitude easier than computing absolute total energies, but it's still hard. So what comes off top of it? What are we missing physically? What are we physically missing? And that is the so-called correlation energy. So I told you the Hartree-Fock model gives you that mean field energy where the electron is swimming in the average field of the other electrons and the nuclei. So what's missing from it is the instantaneous electron interaction, and that is called the correlation energy. Now you can write down the correlation energy exactly as a sum that goes over pairs of electrons. Now, these pairs of electrons, they come in 2 flavors. They come in flavors of pairs of electrons of the same spin and pairs of electrons of opposite spin. Now, the correlation energy that comes from pairs of electrons of the same spin, that is called Fermi correlation. A lot of it is already there in the Hartree-Fock model, and there is relatively little that comes on top of it in terms of the instantaneous electron-electron interaction. That is not hard to calculate. But what is truly hard to calculate is the correlation energy that comes from 2 pairs of electrons with opposite spin. The reason is these electrons, they can come basically arbitrarily close in space. They can even occupy the same point in space. And that is called the electron-electron cusp at the coalescence point of 2 electrons. Now, the consequence of this is, of course, in terms of chemistry, that Hartree-Fock theory knows something about this situation here and is therefore extremely strongly biased in favor of high spin states. So in Hartree-Fock theory, if you ask Hartree-Fock theory whether a given compound is high spin or low spin, it will always tell you it's high spin, always. Yeah, if you ask it for like cobalt 3-hexamine, it will tell you it's high spin, always. Now, in parentheses, I say DFT has the opposite problem. It will usually tell you that everything's low spin. Now, that's why when you do like that mixture between Hartree-Fock and DFT, these hybrid functionals, you combine like the worst of two worlds to come up with like an answer that is much closer to experiment, but for the wrong reason. Now, if you do that properly and you calculate that correlation energy, it's really very hard to do, but it's going to be possible. But this is essentially what is missing. The physical picture here that I have in mind is the following. So where you basically have a sea of electrons that is swimming, and when two electrons just bump into each other, they jump out of the Hartree-Fock sea from occupied orbitals into unoccupied orbitals. And now what you have to calculate basically in the correlation problem is the probability for a single jump, a simultaneous jump of 2 electrons, simultaneous jump of 3 electrons, simultaneous jump of 4 electrons, and so on and so forth. There are very elegant methods that originate from physics, of course, to let you do that. And I'm extremely confident that within a few years there will be standard arsenal in quantum chemistry. So last year we have reported the first couple cluster calculation on an entire protein. So these things are in principle there. They need a bit more development before they're like mainstream usable, but they're on the doorstep, so watch out for them. Good. Now, the interpretation of the Hartree-Fock solutions. The primary result of a Hartree-Fock calculation, of course, is the total energy, and we talked about that, and the approximate many-particle wave function approximated as a single Slater determinant, and we talked about that. Now, but what about the secondary quantities? One of the secondary quantities is the orbital energy, and according to a theory by a guy called Koopmans, that is roughly minus the energy it takes to remove the electron from the molecule. So it is essentially an ionization potential. But again, it's an auxiliary quantity, right? So the things, the physically meaningful things are these ones: the total energy and the total wave function. Well, and the orbitals themselves, I think we talked about them already many times, and I will not make any more words here. Yeah. In practice, they're fun to look at. If you know what you're doing, you can get a lot of joy and a lot of insight of looking at orbitals, but you should know they're not required by nature. There is nothing fundamental in them. Endless debates here. Yeah? You should also know the following. The orbitals are not unique. So when you take the occupied Hartree-Fock orbitals and you do an arbitrary unitary transformation on them, the many-particle wave function doesn't change. So there is not that set of the orbitals, of not even the Hartree-Fock orbitals for a given system in a given state, but you can find an infinite number of possible displays that give you the same information that is contained in that single Slater determinant. So, for example, you can localize these orbitals, and then they look much nicer, and they look like lone pairs and bonds, and you can do that. You're absolutely entitled to do that. They contain the same information as the canonical orbitals that come out of your calculation. Ultimately, you will need to study that a little bit, gain familiarity with it, and read a little bit about it. That's more than we can do. Yeah? What comes out, of course, of the Hartree-Fock calculation is also the total electron density. Total electron density is the sum over the squares of the spin-up and spin-down orbitals. So there is a spin-up density and a spin-down density. That is obviously a weakly structured function here that is always positive, relatively insensitive to bonding. So in fact, when crystallographers solve their problems, they usually, I think, start from a superposition of atomic densities. And that is by eye almost indistinguishable of like the molecular density. There are partial charges and bond orders that come out of it. That is the subject of population analysis. Again, these are things, the partial charge of an atom in a molecule is not a physical observable. If n people have thought about that problem, there are at least n plus 1 suggestions of how to do that best, and there are n plus 1 squared frictions between the people who advocate different schemes. Yeah? I'm in nobody's camp. There are many useful ways to partition the total electron density into like quasi-atomic densities, which will give you partial charges, which you will be able to productively correlate with experiments. Yeah? Again, separate the fact from the fiction. The facts are the physical observables. The fiction are the interpretation aids. And the orbitals, as are partial charges, as are spin populations, as are bond orders, as are many other things, are interpretation aids that help you thinking and help you being creative, but they're not physical observables. Yeah? The easiest population analysis scheme is that due to Mulliken. And when you look at it, you can see that the number of electrons at a given atom can be partitioned into terms that belong to 1 and 2 atoms, and then when you split like the shared density equally between the atoms, then you go to Mulliken. That is being criticized by everybody else in the world, and so on and so forth. Useful schemes are, for example, the natural population analysis or the atoms in molecule theory. Both of these are very good. Proponents of this school here hate people who like this school and the way around. But it's really not worth losing friends over these questions. All of these things are just interpretation aids, and you should be tolerant, and like whatever helps somebody to think is fine, is certainly fine by me. Now, the spin density is a different subject. That is obviously the difference between the spin up and spin down densities. So it is strongly structured. It can be positive or negative. It's highly sensitive to bonding. And this is what you probe in EPR and refined experiments. And so that's why using these techniques you can get that amazing insight into bonding just because it is such a highly structured function. I cannot go into any level of detail here, but I think in your EPR lectures you will hopefully make some connection to electronic structure, because it is very fruitful and it is one of the major sources of knowledge about electronic structure from the experimental world. So, but I wanted to spend like the last 10 minutes or so talking about density functional theory just because of its high level of importance for today's quantum chemistry. Now, the idea is relatively simple. Honestly speaking, I think density functional theory can be viewed as a very elaborate backup or an elaborate justification of semi-empirical theories that have been around for as long as there was quantum mechanics. So Dirac himself proposed some things that by today's standards you would call density functional theory. Nevertheless, Hohenberg and Kohn, they gave, and Charm, they gave a formal framework for that, for which they eventually scored the Nobel Prize. But these things have been around much, much earlier. So now let's grasp the idea. The idea is the following. Now, this is the CO molecule, and we look at the electron density of the CO molecule in a plane. Yeah, so the CO is lying here in a plane. Now, this electron density has two spikes here, two cusps. And one cusp is where the carbon nucleus is, and one cusp is here where the oxygen nucleus is. So the height of that cusp is related to the nuclear charge. So by finding these cusps and analyzing their heights, you'll be able to figure out where is an atom, so where is the nucleus, and what charge does it have. Now, we also know if you integrate over all of the electron density all over space, you find the number of electrons. So, but if you know that, you know the charges of the nuclei, you know their positions, and you know the total number of electrons, you can write down the electron-nuclear attraction operator, which is the only term in the Born-Oppenheimer Hamiltonian that really is carrying the geometric structure. Yeah, so that means you can reconstruct the Born-Oppenheimer Hamiltonian from just knowing the electron density. Make sense? Yeah, so that is relatively easy. So, make that formal. So you know the electron density, you deduce the electron-nuclear attraction and the total number of electrons, so you deduce the Born-Oppenheimer Hamiltonian. Now it comes, here it comes. If you could solve the Born-Oppenheimer-Schrödinger equation, you would know the many-particle wave function and the exact total energy. That's great. I mean, before I started that whole discussion by knowing that and telling you that we cannot solve this equation. Yeah, now I'm telling you we can get to the same point with 2 additional steps. Yeah. 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 Now, basically, the contents of the Hohenberg-Kohn theorems that led you to a Nobel Prize is saying that there should be a way that it's somehow possible to go from here to there directly without having to solve the Born-Oppenheimer-Schrödinger equation. Yeah, so basically it proves the existence of a universal functional E of rho, and it must exist, that leads you from the density to the exact total energy directly, not to the many-particle wave function, only to the energy. That is the first Hohenberg-Kohn theorem, and the second Hohenberg-Kohn theorem tells you that there is a variational principle. That means if you put in a trial density rho prime and you insert it into your wonderful universal functional E of rho, you get an energy that is always too high, and that means if you would know that functional and a trial density, you could apply the variational principle and end up with the exact total energy. Now, of course, everything is like centered around the existence of this wonderful universal functional E of rho. Yeah? Now, since I've tortured you through Hartree-Fock theory, let's see how much of it do we already know as a function of the one electron density. So we know the nuclear-nuclear repulsion because that obviously does not depend on the electron density, so that's easy. So we know the electron-nuclear attraction as a function of the electron density because that is immediate. You can write it like this, so that is trivial. We can have the Coulomb contribution to the electron-electron repulsion. You can write as a function of the electron density with just arguments of electron 1 and arguments of electron 2. That is okay. But we do not know the kinetic energy of the electrons as a function of the electron density. That is unknown. And attempts to formulate it this way, like the Thomas Fermi theory, are failures. And then, of course, what's missing is the exchange and correlation. And so, since we neither know the exchange nor the correlation as a function of the electron density, we're a bit stuck here. So we know 3 things, we don't know 2 things, and we need to make progress here. And a fairly ingenious construction was the one of Kohn and Sham. And so all calculations that you call DFT today are based on that Kohn-Sham construction. So please stay tuned for another 5 minutes, and then I'll be done. Yeah. And so what they have done, so we know that when we talked about Hartree-Fock theory, we talked about a fictitious system of non-interacting electron, and we were using its wave function in order to apply it to the variational principle. Now, Kohn and Sham do something very similar. They invent a reference system of non-interacting electrons for which we know a single Slater determinant is its eigenfunction. But now they ask it to have a very special property. They ask that fictitious model system to share the exact electron density with the exact system. So basically that the electron density that you compute from the Kohn-Sham determinant is required to be the same as the electron density of the exact system. So what it boils down to, if you like, do the math, is that you have a way of computing the kinetic energy to a good approximation by using the orbitals of the Kohn-Sham determinant. So in principle, I mean, DFT says, look, buddy, you need nothing but the electron density. Now, Kohn-Sham comes saying, yeah, if you have that non-interacting system, we also have a few orbitals. Then we only have them because we want to have a density. But then if I, if you let me for a second, please use these orbitals, I can calculate a kinetic energy that's really not so bad. That is a so-called non-interacting kinetic energy. It is not equal to the exact kinetic energy, but it's pretty close to the exact energy. That means, of the two things we didn't know, we have changed it into one thing that we don't know as a function of the density, and that is the exchange correlation term. The true exchange correlation function also contains a correction between the difference of the true kinetic energy and the non-interacting kinetic energy. That is usually swept under the carpet here. And what people then do, and that is every week maybe 15 or 20 new approximations or suggestions of how to construct this unknown xc of rho here. Now, if you insert this all into the variational principle, you end up with a set of equations that very much look like the Hartree-Fock equations, where just like you have the two-electron part replaced by an effective potential, and that effective potential contains the electron-nuclear attraction, the Coulomb term, and then this magic xc potential without going into mathematical niceties, that is the functional derivative of the exchange correlation, functional with respect to the density. Fine. So now here we go. We need an approximation to that exchange correlation functional, and then the entire machinery is basically the very same as in Hartree-Fock. And actually, this is how DFT came into quantum chemistry. People took their Hartree-Fock programs and modified them a little bit and turned them into DFT programs. Yeah, that is possible by the Kohn-Sham construction. But you need to guess that approximate exchange correlation functional xc of rho. And that's such a mess, and because there are no guidelines to doing that, so most of what you have in your computer, in your programs today, comes from first analyzing the homogeneous electron gas, which is something totally unchemical, and then making corrections to that from the slightly inhomogeneous electron gas, which is equally unchemical. And so since this cannot possibly give you good chemistry, then there are empirical parameters. So the most, if you want to say so, accurate functionals that are developed by people like Don Trula contain as many 40 empirical parameters that are fit to huge databases. Now, if you look at the equations that go into these functionals, you will see they're crazy and you don't understand anything there. And I think nobody does. So it is kind of black art. Now, how good are these functionals? And now here I want to just set you straight on what the reality is. If you know the electron density, there is a way to deduce the exact exchange and correlation potentials. Yeah? Now, if you compare them to the ones that are in current use, you will find the following. So this here is the red is the exact exchange potential for the argon atom as a function of distance. And this one is the PBE one, so one of the current approximations. So one thing you will notice that these functions behave wrong in the long range. Yeah, they should behave like -1 over r, but they fall off much too quickly. That has major consequences. These orbital energies that you get in DFT are much too high, much too high, 5-6 electron volts too high, because the shape of that potential is wrong. It also means that weakly interacting systems are very poorly described because the potential here falls off far too quickly. Yeah? There are other failures of severe failures that come from that long asymptotic behavior. It can be fixed, but then you have different problems. But I mean, the real reality of it is if you compare the correlation potentials where here you have the exact one and here you have the PBE one. I mean, you will agree with me that these things have absolutely nothing to do with each other, right? I mean, you could even like take minus the PBE and would have a better approximation than, yeah. So whatever number you compute from DFT is never going to be physically very realistic for the right reason, yeah, because these things are manufactured to be error compensation machines, yeah. There is a lot of really extremely wrong physics in these DFT functionals, and nobody knows so far how to fix them. And that is the reality of it. That is also why I personally think this is not the way forward, yeah, because you should not base a theory on something that is wrong and only relies on cancellation of big errors. Yeah? Having said that, DFT is a wonderfully useful thing to have in your hands, and like theory would not be popular in chemistry if there hadn't been DFT. But one should have a realistic perspective of what it is and what it's not. Yeah? So look, for example, at the following. That is, I think, is a nice example, and I'm pretty much done here. So if you ask yourself, this is like octane and isooctane, so like linear or branched octane. Which ones is lower in energy? Yeah, which ones are lower in energy? So that is these simple hydrocarbons. This is as simple as it gets. Yeah, and I think many people would probably get that wrong, but it's the branched one that is like slightly more lower in energy by about 2 kilocalories per mole. Now, if you ask Hartree-Fock theory, it would put this one lower by 11.5 kilocalories per mole. So that's an error of about like 13 to 14 kilocalories per mole, which, as I told you, is pretty disastrous for chemistry. Now, DFT, in terms of B3-lib or B-lib or so, does the exact same. It is dead wrong. Wave function theory will get that right for you. And the reason for it is that, like, the DFT correlation is entirely short-sighted. Where it comes from that this one is more stable is that there are medium-range correlation effects that go from here to here, so between bonds, correlation effects over 2-3 bonds, and DFT has none of them. And it is also not clear how to fix it. But that shows you that even for the simplest of hydrocarbons, you can easily be like 15, 20 kilocalories off. So if you read those papers where people like start in the title saying my DFT has an accuracy of 2 kilocalories per mole, and this is my reaction mechanism, and that's why you got to believe me, and if you don't believe me, you're a bad person, then you should put that into perspective that even the simplest of things can be pretty wrong. And that's why you're doing science if you're trying to falsify yourself. Don't just believe the computer. Then ask the spectrometer whether it was right what you're thinking in terms of your theory. And then you're doing a much better job. I do believe I have tortured you enough for today. I'm almost out of my voice. And I think it will become more chemical and more bioinorganic from here on. So stay tuned and enjoy the rest of the course. We see each other tomorrow again for vibration spectroscopy.